Today I'm going to show you the problem on 9092 E3. Rectangular wire loop shown above has length C with width B minus A, and resistance R. It's placed in the plane of the page near a long straight wire, also in the plane of the page. The long wire carries time dependent current I equal alpha 1 minus beta times T, where alpha, beta are positive constant and T is time. A. What is the direction of the magnetic field inside the loop due to the current I in the long wire at T equals 0? So current, if we use the right hand rule, current go this way, so and then it's facing up, so the magnetic field is gonna be out of the page. So for A, the page. B. In term A, B, C, alpha, beta, and fundamental constant determine following. 1. An expression for magnitude of magnetic flux through the loop as the function of T. Okay, first we have to know magnetic field, which is B equals mu naught times current I divided by 2 pi R. Okay, but here we have the current, we have the equation for current, which is alpha, I'm gonna write it down, mu naught times alpha 1 minus beta times T divided by 2 pi R. Okay, now we need to do the flux. So what's the flux? Flux is integral of B times dA. Okay, what is dA? In this case, RdA is going to be C times dR. So C times dR. Okay, now I'm just substituting into the integral. So flux equals to integral of A to B from here to here, and what is B? Mu naught alpha 1 minus beta times T divided by 2 pi R times C dr. Now we have to take off our constant. So mu naught alpha 1 minus alpha times 1 minus beta times T divided by 2 pi times C is our constant. Now we have to take an integral of 1 over R times dr. So times integral of A to B 1 over R space to dr. Okay, now what is integral of 1 over R? Is a natural log of R. So again, this is our constant. Just write it again. Times natural log of R from A to B. Okay. Now we have to use the property of log, or just substituting for now, and then okay, times n, natural log of b minus natural log of A. Okay, now our flux is gonna be mu naught 1 minus T times C. Okay, here now we have to use the property of log. So natural log of B minus natural log of A is gonna be natural log of B over A. So times natural log of B over A. That's it. This is for B1. Now we have B2. The magnitude of induced EMF in the loop. Okay, so what is EMF? EMF, well, EMF is gonna be negative derivative of flux to respect to T. Okay, we have the flux here, right? Okay, so I'm just gonna rewrite it, right? So dt mu naught times alpha times 1 minus beta T over here over 2 pi times C times natural log of B minus over B over A. Okay, now we have to take off our constant. So negative mu naught times alpha over 2 pi times C times natural log of B over A. Okay, times derivative of 1 minus beta times T to the respect to T. So okay, here negative C 2 pi times. Okay, now what's the derivative of constant? 1 is 0, and what's the derivative of negative beta times T? So times negative beta. Guess what? We have negative here and negative here, so it's gonna cancel each other. So we're gonna end up with mu naught alpha times C times beta divided by 2 pi times natural log of B over A. Okay, and this is our EMF. Okay, see, show on the diagram below the direction of the induced current in the loop for each of the following cases. Okay, when beta times T less than 1, the magnetic field within the loop point out of the page and is decreasing. So that means we have the magnetic field out of the page. So if the magnetic field is out of the page and we use the right hand rule, so the current is gonna be the counterclockwise, right? So it's gonna be that way. Okay. Let's write it down. C A counterclockwise. And we show it here. 2 beta times T bigger than 1. Okay, now magnetic field within the loop is into the page, right? But is increasing. So when it's increasing and it's into the page, the magnetic field is gonna be out to the page. So the magnetic field of the loop is gonna be out of the page. So if it's out of the page, it's the same as the previous one. Is gonna be counterclockwise. So counterclockwise. Okay, the last one. What is the direction of the net force, if any, on the loop due on induced current at t equals 0? Okay, here. The net force is sum of the forces on the each side of the 4 places on the rectangle. In each case, the force pulled outward of each side. So for the small side, which is B over A, the force magnitude is going to be the same, but the opposite direction. So they're going to cancel each other. So actually, okay, so they're going to cancel each other. But the longest one, which is C, is different. The C near to the current is different to the C the far the current. Okay. Now we have to use the equation of force magnitude. So what's the force of magnitude? The force magnitude is current times length times magnetic field, which is I times length sorry, times B. Okay. For the near side, I'm just gonna call the force 1, which is alpha C times mu naught times alpha 2 pi r. But what is r now is A. R is gonna be A. Okay, and same thing for F2 is gonna be alpha times C times mu naught alpha 2 pi. What is R now is gonna be B. Okay, therefore now A is less than B. So if A is less than B, the force A, which is force 1, is bigger than force 2, which is force acting to B. Oh, okay. It's 2. Force 1 is acting downward, and force B is gonna be upward. But because force 1 is stronger, so it's gonna be down. And that's it.